Okay, in this video, I am going to go through the AQA A-level chemistry paper. It's paper 3, and it's the June 2017 paper. Right, first question then. Anhydrous magnesium chloride can absorb water to form the hydrated salt that we've got there. Suggest one reason why the enthalpy change for this reaction cannot be determined directly by calorimetry. Well, it is impossible to add the water so that some of the magnesium chloride will dissolve. It's inevitable. Some of the magnesium chloride will form, okay, so an aqueous solution, so it won't form the solid. Right, that's the answer to that. Right. So some enthalpies of solution are shown in table 1, and we can use Hess's law to calculate the enthalpy for the absorption of water. So I'll write down this equation. So we're going to get MgCl2 solid plus 4H2O goes to the hydrated magnesium chloride dot 4H2O solid. So we can find this directly by using those values there and a Hess's law cycle. And this is basically required practical 2 at AQA. And of course, this is the practical paper, so that's why they're asking about this. So you should know about that required practical. So the third thing we're going to put down here is aqueous solution of magnesium chloride. Okay, in the required practical, it's actually copper sulfate they do it with, but it's very similar. And what we're doing, well, with this red arrow, we are dissolving the anhydrous magnesium chloride to form an aqueous solution. So we can do one experiment to find that. And on the green arrow, we are dissolving the hydrated stuff to form an aqueous solution. Right, so we can put the values on there. We can see that this red one was going to be 1 minus 155. So this value here. And the green one is going to be minus 39. And we want to find out delta H for this reaction. So delta H, we are following the red arrow. So we stick with that minus sign. And we are going against the green arrow. So we turn that one into a plus. And that gives us an answer of minus 116 kilojoules per mole. That's our answer there. Okay, so again, that is required practical 2, really. Right, 1.3. Describe how you carry out an experiment to determine the enthalpy of solution of anhydrous magnesium chloride. Okay, this is a 6-mark question. And you should use about 0.8 grams of magnesium chloride, and explain how your results could be used to calculate the enthalpy of solution. So again, you've done this in a required practical, so this is why they want you to give the details. Okay, so what are we going to do is we need to have probably a polystyrene cup as the reaction vessel, because it's a good insulator, and it's a good idea to have a lid with that. Okay, and so here's our polystyrene cup. We've got to put a suitable volume of water in there. Well, I would think 25 centimeters cubed would be a reasonable amount of distilled water, and we would probably measure that using a measuring cylinder. It's not necessary to use a pipette there, because the other errors of heat loss and so forth are pretty big, and so it's not really worthwhile going any more accurate than that. So 25 centimeters cubed of water there. Now, how are we going to weigh out the magnesium chloride? Well, you should weigh by difference. So you should get approximately the right amount in a weighing boat. Weigh it before and then tip it in and weigh the weighing boat afterwards and find the mass added like that. Okay, now usually when we do these experiments and in the required practical, what you do is you don't just take the initial temperature and the final temperature you take temperature. Well, I want to draw it as a graph. Okay, so you're going to take a temperature every minute. Here's the temperature, and here is the time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe 12 minutes, something like that. Okay, so you're going to take the temperature every minute for 3 minutes before you add the stuff, okay? And you're going to plot those lines there. At the 4th minute, you're not going to measure the temperature because you are going to add the magnesium chloride there. You're going to add the solid. Right, it's exothermic, so the temperature will go up. And then we record the temperature every minute for about the next 7 or 8 minutes, or until you've got a general trend here. Now, your graph is going to look something like that. How are we going to use those results? Well, we're going to extrapolate this line forwards, and you can see here we're going to extrapolate this one backwards because the solution is cooling down there because it's losing heat to the environment. So what we're saying is if it was losing heat at that rate, then the temperature at 4 minutes when we added the stuff would have been there. So we're going to use that as our temperature delta T. So that's how we're going to find out delta T, by monitoring the temperature every minute and plotting those lines, extrapolating appropriately. Okay. Now it does say how you're going to use your results to calculate your answer. So we're going to use the equation quantity of heat released in the experiment is going to be the mass of water multiplied by the specific heat capacity of water multiplied by delta T. Okay, so that's going to be 25 grams. You're usually given a value of that. So that's joules per gram per Kelvin or degree C increase in temperature. So Q is the quantity of heat released in the experiment. It's not per mole. So but we want to work out delta H solution. So delta H solution is going to be Q divided by the number of moles of magnesium chloride solid that we added. That's okay. So how are we going to find out the moles of magnesium chloride? We're going to find that out by doing moles is equal to mass over the MR. So I think we've got all the necessary information down there to get 6 marks. You do need to have that, that cooling curve thing there to make it work. Right. Anhydrous magnesium chloride can be formed by a direct reaction between its elements. Magnesium and chlorine goes to MgCl2. Okay, the free energy change delta G for this reaction varies with temperature as shown there. Okay, we're going to use this data to plot a graph, and then the question says you're going to work out the gradient of the graph to work out the entropy change. Well, let's just go through the theory of that before we plot the graph. So we know we need to say delta G is equal to delta H minus T delta S. So we plot a line. Let me just get in your equation of a straight line, mx plus c. So if we plot delta G on the y-axis, and we plot the absolute temperature on this axis here, we'll see we get a right. What's the gradient of that line? Well, you can see that the intercept is, which we're not interested in, is delta H. That's C there. The gradient, because we're plotting against T, is going to be minus delta S, because it's got a minus there. So the gradient of the line is equal to the minus the entropy change, and we're going to work out the entropy change. So let's have a look at that. I plotted the graph here. There you go. They gave you that grid with the units already printed on the grid for you, and you just have to plot the line. Okay, so we're going to work out the gradient now. So the gradient is equal to let's call the gradient m, change in y divided by the change in x. Well, I plotted the construction line there in yellow, so let's look at the change in y, delta y. So we can see we've got minus 592 up here, and then there minus, and that is minus 601.8. So minus 601.8, and that gives us a temperature change of delta G change of 9.8 kilojoules. Right, and then we've got to work out delta X. Well, delta X, this yellow line I've drawn here, so that point there to there, so that's going to be 300 Kelvin minus 240 Kelvin, which is equal to 60. So our gradient is going to be equal to 9.8 over 60. That is equal to 100.163. Now the units there are going to be kilojoules per mole per Kelvin. So let's convert that into joules. So it's going to be times by 1,000. It's going to be 163. Now we've said that delta S is equal to minus the gradient, so delta S then is equal to minus 163 joules per mole per Kelvin. And common sense check, that should be about right, because, well, we were forming magnesium chloride from, so we had a solid magnesium chlorine gas going to MgCl, which is an ionic solid, not much low entropy because it's highly ordered. We had a gas here, so the entropy is obviously going to go down, so that minus sign would seem to be correct. Okay, so that is that question. All right, number 2 is a question a lot about sulfuric acid. Okay, concentrated sulfuric acid reacts with alkenes, alcohols, and sodium halides. The mechanism for the reaction of concentrated sulfuric acid with an alkene, well, it is, if you remember, and we're going to do the mechanism in a minute, is electrophilic addition. Outline the mechanism for the reaction of sulfuric with propene to show the formation of the major product. Okay, so now we're going to have propene here. Sulfuric acid has the following structure, so I'm going to do H. Okay, so you've got to remember the, right, that's it. Okay, now the reason why that's an electrophile is because that hydrogen is going to be delta positive, because oxygen is electronegative. Okay, now the first step in the mechanism is for the pair of electrons in the pi bond to go onto the H to form a bond with a hydrogen, and the bond between the hydrogen and the oxygen breaks, both go onto the oxygen to give it a negative charge. Okay, so now we have to be a bit careful because you need to make sure that we stick the H, it can stick on either on that carbon or that carbon. We want to make sure that it's going to give us the major product, so we want to make sure that it actually sticks on this carbon, because then we'll get a secondary carbocation. So I'll draw that. So we've got the hydrogen from the sulfuric acid is now gone onto the right hand side carbon, which leaves this middle carbon with a positive charge. That's a secondary carbocation because the carbon with a positive charge is attached to 2 other carbons. Okay, and if we remember those 2 carbons, and if you remember, secondary carbocations are more stable than primary. You don't have to say that here, but they are. And that's why that forms more, and that's responsible for the major product. Right, also what we've got there now is our sulfuric hydrogen sulfate ion now, just like that. And you've got a negative charge on the oxygen. So that pair of electrons goes onto the carbon there to give us the major product, which is the sulfonated intermediate, sulfonated. Okay, so we've got, and we've got O hydrogen sulfate stuck onto the middle carbon there. Okay, so that's the major product, and I think the next question it's probably going to ask us why that's the major product, or something like that. I'll draw the structure of the minor product first of all. So all we've got to do here is I'll just paste this, I'll copy this. Okay, so the minor product, what's going to happen is right, so there it is. With the minor product, we're just going to have to swap, so to have that hydrogen sticking onto the middle carbon and that going on the end carbon. So I'll just draw that here. So we've got all hydrogens here. And we've got the hydrogen sulfate group stuck onto the end carbon instead. And that will have proceeded through the primary carbocation. I'm pretty sure it's going to ask us about that next. Explain why the product shown in your answer is the major product. Right, so what we need to say is 2 marks here. So we need to say it proceeds via a secondary carbocation. You might want to say the minor goes through a primary. And we also need to say that the secondary carbocation is more stable than the primary, so it tends to form more. Why is it more stable? Well, maybe we probably don't need to say that, it's only 2 marks, but you need to say because it's attached, the positive carbon is attached to 2 alkyl groups, and alkyl groups have a slight tendency to release negative charge, and that is going to reduce the intensity of the positive charge on the carbocation. Right. Okay, so that's that. Right, butane 2-ol reacts with concentrated sulfuric acid to form a mixture of 3 isomeric alkenes. 2 of the alkenes are stereoisomers. Draw the skeletal formula of each of these. Okay. Right, so I'm going to draw butane 2-ol first. Okay, here's butane 2-ol. Now, when we dehydrate an alcohol with an acid, we remove the OH and we remove a hydrogen from the carbon next door. Now there's 2 carbon next doors here, so you could remove that one, and that's going to give you but1ene, or you could remove the green one there, and that's going to give you but2ene. So let's just draw but1ene. So this is if you remove the red hydrogen, so I'll do that in red. You're going to get that. It asks us for a skeletal formula, so I'm going to draw that. So that's the skeletal formula. Okay, now that doesn't exist as EZ isomers, but1ene. It'll give the full name, so that's but1ene. It doesn't exist as EZ isomers because you've got 2 identical hydrogen groups on the carbon with the double bond, so there's no possibility of that. Now let's see what happens if we remove the green one. You're going to get but2ene. Okay, so I'll draw but2ene. So I get the double bond there. I'll just draw it like that. Now you can see there that there is a possibility of, this is where the isom, you get stereoisomers, because but1ene, that one I've drawn there, the high priority groups are on opposite sides, so that's E but1ene, but2ene, sorry, E but2ene. Let's draw a structure of that, the skeletal structure, so it's going to be like this. And there's a Z isomer where I'm going to swap those 2 around, so I'll do that in blue. The Z isomer is going to, you would draw skeletally like that. Now I've got both CH3 groups on the same side, so that's Z but2ene. Okay, so that is all of that done. Now, a byproduct for the reaction of butanol with concentrated sulfuric acid has a molecular formula C4H8O. Right, name this byproduct and identify the result. So let's see what's happened there. Well, we've got butanol, which is C4H9OH, and that has somehow gone to C4H8O. Right, now you can see from that you've lost 2 hydrogens there, so that has been oxidized, and you've actually oxidized the alcohol group to, well, it's a secondary alcohol, so it's going to go to a ketone, so it's going to be that butanol. Now, how has the sulfuric acid managed to do that? Well, we have come across sulfuric acid acting as an oxidizing agent, so that's what it is there when it reacts with halides, okay? Because sulfuric acid, yeah, the oxidation number of sulfur there is +6, so it's quite high, so it can oxidize things. Okay. Now, how could you separate the products of this reaction? Okay, well, these are all ketones and alcohol and alkenes. So it's a liquid at room temperature, so you're going to use fractional distillation to separate it. The sulfuric acid acting as an oxidizing agent there, you know, it's a little bit unexpected, really, because it's never mentioned on the organic specification at all that it would do that. But you've got to sort of make the link where you have come across it acting as an oxidizing agent when it reacts with halides like iodine. Okay, and I think that is the next part of the question, actually. Right, so let's have a look at that. Right, concentrated sulfuric acid, there's a bit after this. Concentrated sulfuric acid reacts with solid sodium chloride. Now, when you add conc sulfuric to sodium chloride, you can't oxidize chloride ions to Cl2. It's not a strong enough oxidizing agent to be able to do that. That doesn't happen. It can oxidize bromide ions and iodide ions, but not chloride ions. All that happens there with sodium chloride is you get an acid-base reaction. So it doesn't ask for the equation, but all that's going to happen is H2SO4 and Cl minus. Well, it gives a proton to the Cl minus, forms HCl gas, and you will get the hydrogen sulfate ion formed as well. Right, the sulfuric acid has acted as an acid there because it's given away a proton. And the observation, whenever you get HCl, you usually see steamy fumes. That's what you say there. You see steamy fumes as you put the conc sulfuric onto the sodium chloride. And the steamy fumes are HCl, hydrogen chloride. Okay, conc sulfuric reacts with solid sodium iodide to produce several products. Now, this is an oxidation, isn't it? So it oxidizes I minus to I2. Right. And in the process, the sulfuric acid is reduced because that acts as an oxidizing agent. And it gets reduced, if you remember, it can get reduced. Well, that's a +6 oxidation number, the sulfur there. It can get reduced to SO2, which is a +4. It can get reduced to sulfur, which is obviously 0, and it can get reduced all the way down to hydrogen sulfide, which is -2 oxidation number. Okay, so the black solid is iodine, I2. The yellow solid is sulfur. And the gas which smells of bad eggs, so that's hydrogen sulfide. It doesn't mention the SO2 there. Okay, so that's that one there. Right, onto an organic synthesis now. Benzoic acid can be prepared from the ethyl benzoate. Okay, so here's the ester, and you heat with sodium hydroxide, you get alkaline hydrolysis of the ester. So you produce the sodium salt of benzoic acid, and you're going to get the alcohol there, which is ethanol. That's ethanol, right? So you got 5 centimeters cubed ethyl benzoate. We're going to use that later, okay? And you add aqueous sodium hydroxide. Right, let's just go through these questions first of all. Okay, all right. So how do anti-bumping granules prevent bumping during reflux? They always ask this question, and the answer they want is it allows small bubbles to form during boiling. Right, show by calculation that an excess of sodium hydroxide is used in this reaction. Right, so we need to look at this bit up here. So we're going to show the sodium hydroxide is in excess. Well, if you look at the ethyl benzoate and the sodium hydroxide, they react in a 1-to-1 ratio. So let's work out the moles of ethyl benzoate here. So first of all, we've got 5 centimeters cubed, and they give us the density. So right, the mass of ethyl benzoate, I just write mass Ester, is equal to volume times density. So it's 5 centimeters cubed multiplied by, the volume is in centimeters cubed here because the density is measured per centimeter cubed, times 1.05. That's equal to 5.25 grams of the ester. So the moles of the ester, that's going to be equal to the mass divided by the MR. So the mass is 5.25, and the MR, they tell us, is 150, which is equal to 0.035. Now we need to work out the moles of sodium hydroxide, which is more straightforward. Moles of NaOH is equal to the concentration times by the volume. The concentration is 2 mole per decimeter cubed, and the volume is 30 centimeters. So that's going to be 2 times 0.03 in dm cubed. So that's equal to 0.06 moles. Now they should be in a 1-to-1 ratio. You can see you've got 0.06 moles of NaOH, which is more than the moles of the benzoate. So the sodium hydroxide is in excess. Okay, so that's that bit. Right, suggest why an excess of sodium hydroxide is used. Well, you just want to make sure that the reaction goes to completion so that all of the ester, or as much of the ester as possible, is hydrolyzed. That's all you need to say there, I think. And now, right, suggest why an electric heater is used rather than a Bunsen burner, and that is just because the ester is flammable. Okay, so it's for safety really, and having a naked flame. Why is reflux used in this hydrolysis? Right, well, we need to heat it, but if you just heated it, all the ester would evaporate, so we need to heat. But the ester is volatile. It's got low boiling point, and that's why you need to condense the vapor using the reflux condenser to stop it just losing everything. Okay. Write an equation for the reaction between sodium benzoate and hydrochloric acid. Okay, so sodium benzoate is going to be, I'm going to write the phenyl group as C6H5, and then you've got, right, so that's the sodium salt benzoic acid. You're going to react that with HCl, and you will protonate the benzoate ion to form benzoic acid, and you will get sodium chloride also. There's the equation there. You can draw, if you want, I think they allow you to draw benzene, you know, if you wanted to draw that instead of writing that, that would be absolutely fine. Right, now why is sodium benzoate soluble in cold water, but benzoic acid is insoluble? Well, sodium benzoate is charged. It's charged there, you can see. And water is a polar solvent. so it tends to dissolve ionic compounds, whereas this is purely covalent. There's no charge in it, so that won't dissolve. Right, after the solid benzoic acid has been filtered off, it can be purified. Right, describe the method the student should use to purify benzoic acid. So really what we're talking about here is recrystallization, which again is a required practical, and the aspirin practical. You have to do a recrystallization there. So how do you carry out recrystallization? Right, you get the impure solid and dissolve, and this is important, in a minimum volume of hot solvent. You don't have to specify the solvent. It could be water, it could be ethanol, just say hot solvent. So minimum volume of hot solvent. So it will dissolve in that, and then you allow it to cool slowly. And the product, the benzoic acid, will precipitate out. Because the solubility is less in the cold solvent, then you may want to put it on ice at the end just to get maximum out of the of solid, so there's less dissolved in the solvent. Now once you've got the solid, that's going to be pure, so then you need to filter it under a vacuum using a Buckner funnel and Buckner funnel and flask. And finally, while it's in there, you want to wash it with a small volume of cold solvent, not hot solvent, because you just dissolve it all, to just remove any soluble impurities. Okay, so that's the recrystallization procedure. You can also filter it while hot, so but you probably didn't do that because it's hard to filter it with hot without losing it, and that will get rid of insoluble impurities. I think you get away without mentioning that and still get 6 marks. Okay. Right. In a similar experiment, so it's a calculation, I think, another student used 0.04 moles of ethyl benzoate and obtained 5.12 grams of benzoic acid. Calculate the percentage yield. Okay. So 1 mole of ester should give us 1 mole of benzoic acid. Right, so how many moles of benzoic acid we should get? We should get, for the 100% yield, is 0.04 moles of benzoic acid. We need to know the MR of benzoic acid. So let's just write. So what we got is C6H5COOH. So C6H5, that all adds up to 77, plus 12 for the carbon, plus 32, plus 1, that gives us 122 is the MR of that. So now we have to do the mass of benzoic acid formed. Moles times MR. 0.04 multiplied by 122, and that gives us 4.88 grams. That would be 100% yield. And how much do they get? They actually get more than that, which I think a lot of people would be thrown by that. Okay, so work out the percentage yield. It's more than 100%. Yeah, so percentage yield is going to be the amount we do get over the amount we expect to get, 4.88, times by 100, and that works out to be 105%. Right, now why are we getting more than 100% yield? Okay, so the most likely thing is that the product contains some water. It's damp. Okay, so you're weighing water as well as weighing the product. Okay, so that's a bit of a mean question, because I think when people did this exam, they said when they came out, they said, I got more than 100% yield. I thought I'd done the calculation wrong, so I checked it again, because they're so expecting, to get less than 100% yield. Right, on to weak acids now. Okay. Right, so I suppose this is kind of related to required practical, where you do, pH with a pH meter, but it's more theory, really. Okay, so we've got 0.1 mole sodium hydroxide, and you add that to 25 centimeters cubed of a solution of weak acid. Okay, so we've got the NaOH in the burette, and we've got the weak acid HX in the conical flask. We've got 25 centimeters cubed of that. All right, they only take the first reading after 20 centimeters of sodium hydroxide solution has been added, so that's why they get that graph there. Okay, now the first question is, it says, the pH range of an indicator, suggest the pH range of a suitable indicator in this titration. Right, you want you want it to change when the vertical part of that line. So you want to have one drop and the color to change with one drop. So we want the pH change to be very rapid. So the range there would be between 7 to about 10.5. You want the indicator to change color in that range there. Give the expression for HX, acid dissociation constant, of course, HKA, H plus its conjugate base, X minus, divided by HX. Okay. Right. That's Ka. Calculate the concentration of HX in the original solution. Okay, so I have to go back up here for this. All right, so we can see that the endpoint is occurring here. That's at exactly 24.0 centimeters cubed of NaOH. So we want to calculate the concentration of HX. So the moles NaOH is equal to conc times volume. They tell us the concentration of the NaOH was 0.1, I think. Yeah, it's 0.1 mole per decimeter cubed, multiplied by 24 centimeters cubed, 0.024 dm cubed. That's 2.4 times 10 to the minus 3 moles of NaOH. Right, NaOH and HX will react in a 1-to-1 ratio, because it's a monobasic acid. It's got one proton. So the concentration of HX is going to be equal to the moles over the volume. So the moles we worked out, they're same moles as NaOH. The volume, well, we had 25 centimeters cubed in the conical flask. So that's 0.025 dm cubed. So that works out to be 0.0960 moles per decimeter cubed. That is the concentration of HX. I think we need that later on. Okay, so remember that. Okay, so we've done that. 4.3, calculate the concentration of HX. Now 4.4, calculate the pH of the solution of HX before the addition of any sodium hydroxide. Okay, so the concentration of HX we worked out is 0.096 moles per decimeter cubed. So how do we work out the pH of a weak acid? Well, we're going to use Ka is equal to H plus its conjugate base, X minus, over HX concentration. Right, so we know, because we haven't added anything to this weak acid, we know that the H plus concentration we can presume is equal to the X minus concentration. Well, also, because it's a weak acid, we're going to say that HX really is not going to be 0.096. It's going to be a tiny bit less than that, but how much of it actually dissociates? Not much at all, because it's a weak acid, so we're going to take that. That's an okay approximation to make. Right, so that gives us Ka is equal to H plus squared, because H is equal to X minus, over the concentration of HA. So H plus squared is equal to Ka, and they tell us the Ka was equal to 2.62 times 10 to the minus 5 multiplied by the concentration of HA, 0.096. That gives us 2.51 times 10 to the minus 6. Right, take the square root of that to give us H plus. I'm going over here now. H plus concentration is equal to the square root of 2.51 times 10 to the minus 6 is equal to 1.585 times 10 to the minus 3. So pH is equal to the minus log of that. It's 2.799. Okay, so 2 dP, that's 2.80 is the pH of HX at the start, 2.80. Right, the next bit now, it says calculate the pH of the solution when half the acid has reacted. Right, this is the half equivalence point. Okay, so you should know that, right? Well, Ka is equal to X minus over HX. Now, when half of the acid is reacted, every time 1 mole of acid reacts, with OH minus, you make 1 mole of X minus. So when half of it, you can say that HA, sorry, I should call it HX, HX concentration is equal to X minus. Right, now when they're equal to each other, that means they're going to cancel out of that expression. So Ka at half equivalence point, Ka is equal to H plus conc. Ka, so H plus, we know Ka because they told us it was 2.62 times 10 to the minus 5. So take a log of that, minus log of that, and we get 4.58. The pH is 4.58 at the half equivalence point. Now, what we've got to do now is plot those values that we worked out. So the pH, this one at the start, 2.80, and at half equivalence point, we've got to plot them on the grid. Okay, so let's do that. So I've pasted the grid in again, and we're going to complete this missing part of the curve between 0 and 20. So a half equivalence point, which will be, now equivalence point is at 24 here, so we want it at 12. Okay, and the pH there is 4.58, so at 12, which is here, 4.5. 4.58, so that's 12. Where are we? About there. And the pH at the start was that was 2.8, so that's right down there. Now you've got to do those. Now you've got to, if you just drew it as a straight line like that, you wouldn't get all the marks. Okay, because what always happens is there's always a bit of a sort of S shape. You always goes like that. I'll do it in a different color, green. Yeah, it always goes up steeply at first a bit, and then it kind of does that. Okay, so you've got to have that sort of like little dip, that little S bit to get the mark. Okay, that's the answer there. Right, and I'm going to leave it there because the next bit is the multiple choice questions and it will make the video too long if I do them. So I'm going to do that in the next video instead.